And so this is your z-table that you can find on Canvas. Um, the way this table operates is there are z-scores listed on the perimeter and areas or probabilities listed on the inside. If you forget that fact, it's conveniently reminding you right here in this picture. Notice it's saying the z-score is on the outside of the picture, the area is on the inside. Same thing, the z-scores are on the outside, the area is on the inside. It is also always going to give you area to the left, again, as this picture is showing you, which is a less than probability. It's going to be important later because anytime we have a greater than probability, we're going to have to work with a complement. Okay, now how we work with this table is if we want to find the probability that z is less than, again as the picture is indicating less than, some z-score, we find that z-score on the outside of the table, and then we go to the inside to see what area that is. The tenths place is listed in this column, the hundredths place up here. So if my example, as we see in this first problem, says find the area to the right of negative 1.22, I'm going to have to find negative 1.22. I see negative 1.2 right here. And then the hundredths place, I have to find which column I want. I want one negative 1.22. That's this one right here. This would be where the second decimal place is at 2. So I want the intersection of those two lines me up for the area that corresponds to that z-score. And again, remember, that's the area to the left. And so when we work this example, we're going to do the same things that we had done previously. We're going to write a probability statement. Make sure you catch here that even though the question doesn't say find the probability, it does say find the area. And remember, with a continuous distribution, area and probability are synonymous. How do I know I'm in a continuous distribution? Because the question says find the area to the right of negative 1.22 in the z distribution. And we know that the z distribution is specifically the standard normal. It's a normal distribution, mean of 0, standard deviation of 1. Normal distributions are subsets of continuous distributions. So I'm being asked to write a probability statement, and I'm going to write this as the probability that z is greater than negative 1.22. I did greater because that's to the right. So if I were to just draw the picture, I would draw a bell curve, find negative 1.22 on there, and then I want the area to the right of that. Notice because it's a z, my bell curve would peak, that middle would be 0 because the mean is 0. And we know in symmetric distributions, the mean, median, and mode are all the same. So my line would be to the left of 0, and then I would shade to the right. Now, as we talked about, looking at that z-table, it always gives us area to the left. This is area to the right, and so I have to work with the complement. If I work with the complement, it allows me to change the sign in the probability statement as long as I tack on that 1 minus in front of it. So I'm going to rewrite this as 1 minus the probability z is less than or equal to negative 1.22. Now, I want to make sure you understand here that or equal to in the z probability statement is actually irrelevant. Why is that? It obviously was not irrelevant in a discrete distribution. That is because in discrete distributions, the variables can equal whatever that number is. So in the discrete distribution, x could be 2 or 3 or whatever. In a continuous, it cannot. As we talked about, the probability that x equals any number is always 0. So whether you have an equal to or not doesn't actually change the work in this problem. Okay, I'm writing it out here to be correct because we work with a complement. The complement of greater than is less than or equal to, but the or equal to doesn't matter. So I can then rewrite this as 1 minus, and now this is what gets replaced with that number inside the table that we just found of 0.1112, subtract that from 1 and I get 0.8888. This is important to make sure you understand that the z-score goes inside of that probability statement. And when I go to my z-table, I am replacing the entire probability statement. Why is that? Because when I go to that z-table, I have converted the z-score to a probability, and specifically I've converted it using a less than probability. That's why I had to rewrite the probability statement to a less than, and then I can replace that whole thing with that number. I don't replace the negative 1.22 with that. So this is where you can really show that you know what you're doing or not based off of how you write your probability statements. It's very important getting good habits right now the problems are simple and you can probably just look at the table and do some things, but I'm going to get questions about why you got an answer wrong on the homework, and it's going to be you subtracted from one when you shouldn't, or you didn't subtract from one when you should, because you're not being careful with your probability statements. You're not writing it out. If you write it out and follow through logically, it works pretty simple. And obviously it looks simple when I'm doing it. That's why it's a good idea here to go ahead and pause as we get to these examples and see if you can work through them yourself and find other examples to work through as well, because we want to make sure that we're dotting all of our I's and crossing all of our T's here. Work everything step by step. I can rewrite it this, like this, like this, like this, and keep moving forward. And understand that negative 1.22, which is that z-score, I replace that entire probability statement with what I found from the table to give me my answer. Notice I can ask the questions to find the area to the right of, find the area to the left of, find the area in between, or I can just give you the probability statement straight off the bat. So this is actually a little bit easier in that regard because I have the probability statement written for me. And you say, okay, I know how to work with a less than probability, because if it's less than, I would just go right to the table, right? Because that's what the table gives me. I can just go to that z-score, boom, we're good to go. If it's a greater than, I got to go to the table, but I got to subtract from one. How would I work an in-between? And the trick that we're going to use is that we're going to rewrite our in-between probabilities, where we're going to say it's the probability that z is less than the big number subtracted, then subtract the probability z is less than the smaller number. And it's going to look like this. And this is a little bit weird. You might want to pause and take some time to rectify this in your brain and make sure you understand what this is saying. A lot of people get confused because they want to put this number here and this number here, and it doesn't work that way. Why this works is this is an area in between, clearly, these two numbers. And so if I start off with the probability z is less than 2.1, if you were to draw this out, if you draw out the probability z is less than 2.1, you would get this picture, except it would go too far. And I hope that makes sense to you, because this is going to have a right bound over here at 2.1 and the left bound at negative 1.22. When I do this, it's going to have the right bound at 2.1, but it's going to go all the way to negative infinity. That's the problem. I went too far. Notice I have too much area here, which is why I have to subtract off what I've accidentally counted extra. And that's the area to the left of that negative 1.22. Another little kind of trick you can use to remind yourself, we're subtracting. This is like the idea of a complement, and that's why this z greater than negative 1.22 becomes z less than or equal to negative 1.22. It's that complement idea. If that didn't make sense, that's fine. As long as you remember it, there's lots of different kind of tricks you can use to remember how we can work this problem. And then from there, it's simple enough. I have to go to the table, and I'm going to look up 2.1 on the outside. I'm going to look up negative 1.22 on the outside, replace the entire probability statement with those two numbers, and then just subtract off to get the answer. And then our last example is a little bit different. It says find the value of z, lowercase z, such that the probability that z is greater than this lowercase number, whatever it happens to be, is 0.1. Notice in the first two questions, I'm asking for probability, or I'm asking for area, which is synonymous with probability. And notice in this case, I'm given the probability. Notice the probability is 0.1. You see that the probability is equals 0.1. I have a probability. I don't need a probability. What do I need? I need a cutoff value. Notice in the problems before, I was given the cutoff values. The cutoff values were negative 1.22 and 2.1. So I have to go backwards. Okay, I have to do everything the exact opposite of what I did before. And so in this case, rather than saying I have a z-score, I need a probability. That meant I go outside in. Why is that? Because the z-scores were on the outside. And then I go to the inside. Now I have a probability. I don't have the outside. I have the inside. And I need the outside. I need the z-score. I need to go the other direction. So instead, what I'm going to do is I'm going to have to look up a probability on the inside of the table. But notice again, I have the same issue here that I had above, in that my area on that z-table is always to the left of, which means that I need a less than probability. Notice this probability statement is greater than. So instead, what I'm going to do is, as before, I'm going to work with a complement. How do I do that? I rewrite this probability statement, as, and this is a kind of one of those algebra 1 tricks, right? If you add 3 to one side, you have to add it to the other side. So I'm going to work with a complement over here, which means I have to work with a complement over here. That's how equalities work, right? So I'm going to work with a complement here, which means change my sign. I have to work with a complement over here. That means since it's a probability, subtract from 1, and that's the 0.9. And now because I have a less than, now I have the appropriate probability. I go to the inside of the table, and then I have to see what z-score that corresponds to. Notice at this point, I want to find the closest value. Okay, don't worry about rounding up, rounding down, just find the closest value to 0.9. And if I do, that's going to be on the row of 1.2 and the column of 0.08, which tells me that the z that I'm looking for is 1.28. The next page of examples would be ones that I would have you work on your own, give a little practice, see if you can do this. And these first 3 examples here, if you hadn't seen them before, might have been a little bit newer. But now that we've seen them, you've kind of seen all the tricks. So make sure you pause and try to work through some of these next examples, see if you can do them on your own. You have all the tricks at this point between how we work with complements, how we know if we're going inside out or outside in, etc. And so we start off with find the area to the left of negative 1.4. This one's a very straightforward question. To the left means less than, so I'm going to write out my probability statement. Probability z is less than negative 1.4. And in this case, I just get to go straight to the table and find that value. Next one's probability z greater than 1.51. So now I need to rewrite that probability statement because the table only works as less than. So that's 1 minus the probability z is less than 1.51. Now I get to replace that with a value from the table to arrive at my answer. And then we have an in-between probability. We're use that trick we talked about previously. This is going to be probability z is less than 4.12 minus the probability z is less than or equal to negative 2.18. Notice if you have a z-score that runs off the table doesn't actually include it. You're just going to use the most extreme value in your table. Some tables that's 0.9999. This one it's 0.9998. Not a big deal. You're not going to get counted off. If you're off at the 4th decimal place, you will. If you're off at the 2nd or maybe the 3rd, but the 4th one will be fine. So if you use 0.9999 there, that would be fine. Not something to worry about. But again, if we have a z value that goes off the table, then just use the biggest or smallest one, whichever one's closest. Then we have a series of examples that work the other direction. Find the value of z such that we have a greater than probability equal to 0.025. As before, this is a greater than, so I need to work with complements and look up the value closest to 0.975 in the table, and that would be 1.96. The next question says find the 99th percentile. Here, notice I've worded it a little bit differently, but we should be able to come up with a probability statement here. If we recall from chapter 2, a percentile is defined such that it's the cutoff where that percentage of the values are less than that. So this works out really well because a percentile is a less than probability, and our table works less than. So we just get to go straight into the table now and look up 0.99 because we already are working less than. We don't have to do a complement. And that would be z equals 2.33. The next one's similar, and it says find the first quartile of the z distribution. And in this case, you'd have to ask yourself, well, what is the probability that we're going to be looking for? And again, now we have to go back to chapter 2 and remember what is a quartile. A quartile is the value such that 25% of values are less than at 75% or bigger. Remember, our first quartile cuts the bottom quarter off. The second quarter cuts the bottom half off, that's the median. The third quartile cuts the bottom 3/4 off from the top quarter. And so I just get to go inside the table and look for 0.25 to find the z-score. And then the last one is a similar idea, but now instead of giving you a probability statement, I've worded it out just like our very first one that we had. Find the area to the right of 0.65. Just want to make sure that we don't get in too much of a rut here. This would be a probability that z is greater than 0.65. I have to work with complement, and that would be how we finish that problem off.